I'm Jing, and I will talk about the always-on localization for Project Aria glasses. So first, what do I mean by that, and why do we need it? In order to build light maps, which is a digital representation of the world, we need to fuse all the available sensors together from different users and back in the history. And to enable such sensor fusion, the first step will have to align all the historical sensor observations from different users into a common space-time frame of reference. And such space-time of reference is required to be millimeter, millisecond, and median radians accurate. Now, is that a solved problem? Well, to some extent, yes. Here I'm showing a video showing the Oculus Insight running on the Quest headset, which we worked together with the Insight team over the last few years, and it actually works incredibly well. But if we're thinking beyond a single house and look at Aria data we have already collected, the pictures changes quite a bit. First, there are many challenging scenarios, as I shown some example here, like biking, swimming, driving, or very dark in the night. Such scenarios are very hard to be solved the space-time reference problem. Second, some are even daily scenarios. For example, how to build a map to handle the environment variation across different time of the day, different seasons, or different weather changes. And third, some requirements are must-have for future AR glasses. For example, small form factors, power consumptions, which limit the sensor choice we can use, and also privacy requirements, which I will not dig in too much into that, which Armin and Hyujin will give a talk about that later. And all these requirements, we are looking at how to solve it. And those are already on top of the state-of-the-art solution we are already provided today, as announced by Zhaoyang and Pierre that the machine perception system has a VIO trajectory we are providing today, and the dataset also with the trajectory. Before we dive into our actual research, I want to introduce a very useful framework here, that we are solving the problem of a space-time reference frame into estimating a joint probabilistic distribution of the world, which the state of world, including the location and the calibration of the devices, and also the surrounding world, which just the maps. And we're estimating such state not just in the current, but also back in the history. And now we have two types of different sensor information source to solve this problem, to work with. First, the sensor observation of the world. This includes the image we have taken, but also includes the sensor information such as IMU data, Wi-Fi signals, or even the audio sound of the environment. And secondly, the prior knowledge about how the world is distributed, which is essentially allow us to complete and denoise anything that we cannot directly observe from the sensor data. And such breakdown is just very obvious of the base rule. A real example using this framework in computer vision, which is a dense optical flow problem, which people here are very familiar with, that we know that optical flow is an ill-conditioned problem in the uniform area, which the sensor data is not enough to estimate the unique solution. Instead, to estimate optical flow in the unique area, we need some kind of prior information, for example, simple uniform prior, or the prior get from machine learning to get a solution. And I will give a few examples how we use this framework to solve our localization problem. Project Aria devices enabling sampling the human experience everywhere and always, and that's why it's a very powerful tool help us to collect the right data and enabling the research. And for our localization research, the value of Aria devices are first, as a data collection vehicle, it provides a different type of sensor data we can use to observe the world in many different ways. And second, thanks for the comfort provided by the Project Aria devices. The Aria program is able to collect a large amount of data from many user daily activities and providing the researcher with a representative and exhaustive egocentric data set, which is massively useful for us to learn what the human motion looks like. And as discussed by Zhaoyang before, the project Aria glasses give us a variety of user sensors. For example, images, which here is a computer vision conference, so we mentioned that, and also the IMU sensor, which is people widely known using the SLAM problem. However, today I want to talk something less obvious, that how do we use the Wi-Fi signal help us to solve the localization problem. Addressing the visual ambiguity is one of our core use of Wi-Fi information. Here I'm showing 10 different conference rooms, which they all have very similar visual appearance, at least from the human perspective, which is hard to be distinguished. And also, our visual localization algorithm can easily fail into just localizing into a wrong room. And what we do is we embedded the Wi-Fi information on top of our visual inertial maps, enabling us to solve the Wi-Fi, to use the Wi-Fi SSID and signal strengths to perform a coarse localization fully on device. And such coarse localization can be used to guide the fine-grained visual localization later. Here we show some coarse Wi-Fi localization result in both outdoor and indoor dataset. And we can see that we get overall better than 5-meter median accuracy, which is more than enough to guide our visual localization. And here I show some real-world example how Wi-Fi helps us to reject false visual localization into a wrong conference room, as I mentioned before. On the left side, you will see that the query recording localized into a visually similar room, but which is wrong. And on the right side, we can see that the same recording does not localize into the wrong room with the help of the Wi-Fi information. Other than the sensor on the Aria devices, it's actually possible to use sensor outside the glasses to help localization. In this slide, we solve that how the extra sensor data can be helpful to solve the moving reference frame problem. Here we're showing some results collaborating with BMW, in which we pair the extra IMU sensor on the car with the Project Aria devices. In the slides, we show the car lock rendering results with the help of the car IMU. And actually, it's allow us to not only localize the user in the car, but also help to localize the car in the world, which enabling both car lock rendering and world lock rendering for AR experience. Back to the moving reference frame problem. There are common cases other than car in which we don't have extra sensor data to use. A very common problem is elevator, which I believe most people here have taken at least one elevator ride today. And pairing every Aria glasses with every elevator you walk in the day will be quite impractical. However, we know the elevator has very special motion pattern, which is it simply moves straight up and down. And given this strong prior knowledge, we can use to track the people's motion not just in the elevator, but also we can track how the elevator moving in the space. And here we show the video of both of the results, that how the user moving the elevator and how the elevator, the red box, moving in the space. Next, other than the handcrafted prior, like the elevator cases I mentioned, I will show how the machine learning can be used to learn the motion prior. Most modern visual inertial odometry method has two major components: an image processing block, which extracts a visual correspondence, and also a state estimator like a Kalman filter to use IMU data predict over time and use the visual correspondence to correct the estimate. The extra information from the vision is very important to this inference since the existence of unobservable states, and also this visual information is very helpful to reduce the long-term drift. However, sometimes vision correction is not always available for multiple reasons. For example, the crowded environment with moving people around, the environment is too dark, the camera is turned off for privacy reason, or simply you want to reduce some power. Without variant correction, the prediction using IMU becomes simply a noisy double integration, which can quickly diverge in a few seconds. In the work of tightly learned inertial odometry, TLIO, we demonstrate that the correction needed for state estimation does not have to come from the extra sensor data, like camera, but it can be the pure information we learned from the historical data. The human egocentric motion has very common patterns, like sitting, walking, and running. Those common patterns can be captured by the machine learning algorithm and in the future used to correct the motion prediction. And in the TLIO, we trained a neural network to learn those patterns. The neural network is capable to recognize these common daily patterns and to correlate them into the motion they likely have to using the IMU data. And the neural network's output is then sent back to the probabilistic state estimator, in our case as a Kalman filter, as a prior information to help to estimate the unobservable state and reducing the long-term drift. We demonstrate how great those learned prior works. In a long-term tracking example with only IMU data, the median translational drift is about 1.5% of the total moving distance, which is about 2 times better than other state-of-art IMU-only estimation. Now, all this result we're showing here is trained only with about 40 hours of data. But with the project Aria provided a large amount of data, we will have much more data and much more diverse environment to learn. And later, we will continue working on this track and delivering more results later. Other than the human motion prior, another type of prior information we can learn is how the world is like to change over time. We call that map persistence prior. There are many entities in the world are not persistent over time, likely to change in minutes, hours, or days. I'm giving a few examples here as shown in the image. Non-persistent objects like chairs or the small objects on the ground, those stay in their position with only hours or days until next time people move it. And another common case I'm showing here is the shadows, which shadows in general only stay there less than minutes. Those temporary objects and textures are not useful for long-term localization because they disappeared in the amount of time. It makes sense to remove them in the map, but a better way to approach this is we do not even put them in the map at the beginning. And that's why we have the research of persistent prior learning, in which we want to identify those non-persistent objects and texture as early as possible, other than we have to wait hours, days, or weeks, and then remove the dead content from the map. We first built a data set from the Aria data we collected over multiple months, across different time of day and across different weathers. The collected Aria recording are further processed to build a map, and each map point automatically annotated how long those points stay in the map. And we show some maps we annotated in the outdoor cases. And we can see that although most of the points last more than 6 days in the map, which has mostly the structures on the buildings, there are plenty of points lives less than a few days. And given such data sets, we train a neural network to predict the per point lifetime. And the result can be used to tell whether the point is useful for long-term mapping or not when we just detect this point. Here we show some results using red point to mark the map point has been identified as non-persistent. And we can see that movable objects like bikes, signs, and humans are marked as non-persistent, while there are only a few points on the ground, and most of them are shadows, which are not persistent for sure. And this year in CVPR, we have a paper accepted about how to learn this map persistent prior, and please check out in the poster session. And at the end of my presentation, I want to thank the team, and now we go to Q&A.
Yeah, let's use the mic in the center of the room for Q&A.
So, good talk. I had a question about the IMU, like learning human behavior on IMU. But if you just use IMUs, right, you take out the vision part, which is loop closure and model adjustment. So is that, like, are you able to solve IMU plus camera? Like the level of estimation you get from VIO, are you able to do better? Or like what is the baseline compared to just learning human behavior on IMU?
The motion we learned, which is the input data, which comes from all the sensor field together. So we are learning a visual inertial trajectory, which including all the loop closures and all the variant corrections. Okay. So what we learn here is a corrected version. Okay. And that's a prior we're taking. And when we take that in, when we do the prediction, we only use IMU data. But with all the fitting trajectory with variant correction, the prediction itself is better than just doing the IMU double integration.
But is it better than doing IMU plus camera?
It is not. That's what I say, that we have about 1.5% translational error, which is for sure worse than the state-of-art visual inertial. But you know that we don't have images in it. We're losing a very strong correction. So using IMU only, getting that 1.5% is pretty impressive, at least to me. So, yeah.
That's impressive, that's for sure. But I was asking in terms of like how that is doing compared to like just taking vision out of it. Yeah. You know? If anyone has a question, I have another question.
Sure.
Sorry. Yeah. So my question was in general about VIO and what your opinion is on. Like, so if you take like scenarios that are not like just moving around a scene, like let's say like running around, or like things that require a lot of jerks, like a lot of like high-speed motion, where the brightness consistency assumption is like lost in terms of like trying to do, let's say even optical flow, right? Does like, because the frame rate for a camera is around 30 frames a second, and the IMU frame rate is around 200 hertz, right? Mm-hmm. Is there a need for doing like high-speed visual odometry, or is that like you're going to get the same amount of results if you have more frames?
Let me repeat the question. So the question is, in the high-speed motion scenarios, whether the images are helpful or?
Oh, I'm saying like having more sampling in the images.
More sampling of the images.
Yeah, because then like translation of the data points are not that far away, right? Like the features don't move that far. So is like having high speed, like, because the IMU does 200 hertz, right? And your camera is doing 30 frames a second. And then let's say,
whether more images are more helpful.
Yeah, more images are helpful.
Oh, for sure. The more information you have, the better you will get. Yeah. And the smaller the image features moved, the easier you can build correspondence between them. So yeah, we want the higher frequency as possible, but it's also limited to like the hardware, the energy. So that's a trade-off across the algorithm and the hardware side.
Yeah. I mean, I was working on that problem, so I was just trying to get your opinion on it. Okay.
Yeah.
Thank you.
Cool. Thanks.
All right. Thanks a lot for sharing all your work, guys. I have a question for Jingdang. You mentioned a little bit about kind of like doing localization within the car, and also around like external sensors. Yeah. Could you maybe like kind of talk a little bit about that?
Talk about how do we do that exactly?
Yeah, like how do you guys like kind of interface like Aria with like external car sensors?
Oh, so I mean, how do we interact with the car sensor? Yeah. So that's more to a technical detail, which we collaborate with BMW. So they expose some car sensor which not exposed to the general public or not their collaborator. And we collect both sensor data together, which we can stream Aria data down. We stream the car sensor to some place, and we record them in the VRS together. That's how generally we do that, and we process this offline right now.
Oh, okay.
Yeah.
Cool.